degree in Chongqing National University. So I will be presenting about the estimation of BOG evaporation rate and LNG heating volume from LNG storage tank using dynamic simulation. So the content of my presentation, first is the problem description, the LNG storage tank cases, process simulation, the dynamic simulation output results, and summary execution. So first is the problem description. So here's the LNG storage tank with a temperature of negative 162 degrees Celsius, and the heat is transferred from the outside air to the tank, and the methane evaporates, and BOG is vented. And as BOG vented, the initial heating value is increasing. So our task is to estimate the span time to approach the LNG heating value to around 10,600 kilocalories per standard cubic meter. So this is a problem given by CODES. And we have this simulation assumption. So the LNG tank is assumed to be dome roof type, and BOG is assumed to be venting by a control valve. And there is no LNG feed from the outside. Only BOG has been generated by the feed exchanged with the outside air. And the heat transfer associated with the current time stream default value has been applied. And one of the system is N2 blanketing system for LNG tank operating concept. So these are the LNG feed composition and conditions for each cases. And we have estimated the gross heating value using Pro2 and then using line stream. And these are the ambient conditions for summer and for winter. And these are the operating conditions of LNG tank. And for the storage tank cases, so these are the factors affecting the methane evaporation. So this is calculated based on 100% pure methane, and it is calculated based on the maximum temperature in summer and the minimum temperature in winter. For case 1, we have this capacity of the LNG tank, and for case 2 and case 3 as well. And it has an approximate these are the approximate BOG per day. These are the tank conditions and surface area of vessels for each cases. And then these are the surface temperature and heat transfer rate for each cases for summer and for winter. And these are the summary of data and calculation of the heat transfer coefficient. So we use this equation to calculate this heat transfer coefficient here using the previous values. And for the process simulation, so we use this thermodynamic model, Penn-Robinson. And this setup is for the LNG storage tank with the help of invencies. And with the simulation in freeze mode with the input parameters. And these are the simulation procedures. So first, we modify the compositions for each cases, and then we adjust the tank size, the height and diameter based on the specifications from CODES. And then we manipulate the ambient temperature based on the minimum and maximum temperature in winter and summer season. And then we vary the heat transfer coefficient based from the calculated value of HTC using the data from CODES. And then we adjust the set point value for the liquid level based on the value of the tank inside height. And then we fill the tank until the GHB value reaches this value. And the start time wherein the tank was already filled will be the initial GHB. And then we stop the dynamic simulation after we reach this value. And then we record the time spent to reach the heating value from heating value of 10,600 from 10,300 kilocal per normal cubic meter. So first is, this is a dynamic simulator. So we modify the composition for the different set of cases. So these values are changing. And then we adjust the tank size. And then we manipulate this ambient temperature depending on the season. And then we vary this heat transfer coefficient. And then we adjust the set point parameter for the liquid level. And then for case 1, so this when the tank is already filled, so the GHB value here is around 10,300. But the natural value here is lower. And for case 2 is also almost similar as case 1. And for the third case, almost similar. And for the dynamic simulation, so we need to reach 10,600 here. So for the dynamic simulation output, for the first trial, we used the default heat transfer coefficient in Dynamium. And when we use that default value, the BOG evaporation rate from LNG storage tank is too high. And this is the estimation of time, so it takes about 5 hours to reach this final GHB. So these are the summary for trial 1 using the default heat transfer coefficient with N2 blanketing. And then for trial 2, we try it without the N2 blanketing. And just a similar result was obtained, so we didn't do the simulation for case 2 and case 3. Then for trial 3, we used the calculated heat transfer coefficient with the same initial liquid level for each cases. And these are the results. But it shows some inconsistency with the spend time. Because the spend time should be increasing for each cases, but here it decreased here, and then increased. So there's a little bit inconsistency. So we try another trial for case 4 using the different initial liquid level for each cases. And this is the final result. So the spend time is increasing for summer. And these are the BOG amount per day that is obtained. And then for the summary and conclusion, so we just tabulate the data for the comparison for each cases. And these are the comparisons of the BOG evaporation for, based from focus result and our Dynamium result. And for our conclusion, the compositions of LNG for each case give different values of GHB, but only have little differences. And when the Dynamium default heat transfer coefficient was used in the simulation, the BOG evaporation rate resulted to a very high value of flow rate. And when the calculated heat transfer coefficient based from TOGAS data was used in the simulation, the BOG evaporation rate obtained was almost approaching the results obtained from TOGAS. And it takes longer time to reach the GHB value from 10,300 to 10,600 kilocal per normal cubic meter for winter season compared to summer season. And the BOG evaporation rate and total heat leakage have lower values for winter season than summer season. And there is no significant difference with or without N2 blanketing since same results are obtained. And for further studies, instead of using the maximum and minimum temperature in summer and winter season as the ambient temperature, average temperature for each season can also be used. And for the heat transfer coefficient, only the natural convection heat transfer from the fluid to metal wall was calculated and applied in the dynamic simulation. The calculation of the heat transfer coefficient to ambient can also be considered. But in the previous simulation, the Dynamium default value was used and can be changed for further simulations based on the calculation using per life as insulation. And lastly, increasing the storage days can be proposed through simulation using other insulation materials with a lower thermal conductivity than that of per life. So thank you for listening, and I hope you understand the presentation.